Okay, good morning, welcome to
KidMath74.
KidMath74. So today we're going to start probably a 5 or 6 movie series about quadratics and cubics. Sorry, I didn't erase your brother's movie that well. You asked me yesterday, you had a question about the cube root of 343. And that, do you remember what that is?
It's 7.
7. And you were wondering why, if we have something like the square root of 49, we can talk about plus 7 and minus 7. That comes up in our quadratics. But why we didn't have multiple solutions here. Right? Because, for example, negative 7 cubed is what?
Negative 343.
Yeah, so it creates a little problem. So we're going to study some graphs in general. So the first thing I want to talk about seems kind of like a subtle point, but it's actually important. To simplify things, we can always divide by a here, as long as a is not 0. So we could just change this into studying x squared plus b over ax plus c over a, and then similarly we can do something similar with the cubic. Okay. And first I just want to explain what that's going to do for us. So we're going to, if we just have y equals x squared, I was supposed to touch here.
Big dot.
Need a big dot. If I scale it up, if I multiply by 2 or 3 or something bigger than 1, I get a curve that's steeper. If I multiply by something that is between 0 and 1, still positive, but just less than 1, I get something really wide. And then when I multiply something that's negative, it just flips the whole thing upside down. So if it was between 0 and 1, but negative, between 0 and minus 1, something like that, and between 1 and infinity, but negative 1, negative infinity, I get this curve. Okay. And if a is 0, if I multiply by 0, I just get this straight line. But
linear. Sure.
We don't want to study lines. Okay, so this seems like a subtle and maybe even a little bit, why am I even bothering to talk about this? But I want to say we can just simplify our discussion to talk about things where the leading coefficient's 1. Okay, because the shape broadly stays the same. Might get a little steeper, might get a little wider, but it's the same shape.
Yes.
Okay. So we have found, when we have real coefficients here, like x squared plus 2x plus 7 or something like that, we found 3 cases. One where we really do stay above the axis. No amount of big dots is going to solve that. One where we touch the axis. Oops.
Now we need a big dot.
Now we need a big dot. And one where we hit the axis twice. So I can have 0 roots.
0 real roots.
0 real, thank you. Good correction. Good correction.
Because those are imaginary roots.
You can have imaginary roots, and that's what probably we'll talk about that tomorrow, even though tomorrow is
Christmas.
You can have 1 root, or you can have 2 roots. Okay. But cubics, we found something a little bit different. So we're going to use 1x cubed and then plus bx squared plus cx plus d. Okay. We found a very different behavior, right? Y equals x cubed comes in, looks totally flat, goes down here. We found some other ones that seem to come up and then they don't go flat at all, but they bend a little bit. Then we found other ones. Draw a couple other ones that we found when we were playing on Mathematica.
Something like that.
Yeah. And then we could shift this down here, for example, and have it go like this, too. Okay. So what are the different number of roots we found?
Well, we know we can have 3 roots.
We know we can have 3. We found some that have 3, definitely.
And we can kind of envision a case with 2.
Okay, how? Show me how you would envision that.
Well, just shift this hump down to here.
Have it just exactly touch. Okay.
And then you can have 1 like
well,
this.
now let's draw that just so it's clear. Actually,
a blue maybe?
Sorry, our graph is getting a little unwieldy,
Right.
but it's going to look like this. It's going to go up, just touch the axis, and then go like that. And let's say our y-axis is there. So touches the x-axis there. So that has 2 roots. So we can imagine one with 3. We got that. 2. And then can we imagine one that has 1 root?
There's 1 drawn right here.
There's 1 drawn right there. But what was the problem?
We can't have 0.
We can't find any that have 0. So that is a qualitative difference between cubics and quadratics. Because with quadratics we could find ones that had 0 real roots, as you pointed out. Now, let's talk about this shape when we have a leading x cubed. What did we find was similar between all of the graphs where we had an x cubed, and that helped us at least give a reason why we thought we might always have at least one root?
Because we figured that this goes down for infinity, and then this comes up for infinity.
Okay, that seemed to be the case on all of them, right?
Yes.
We even tried making this term here on the x squared really huge to give us really big numbers to try to cancel out the x cubed, but it never seemed to. We even went up to 1,000.
Yeah, maybe if we made it infinitely tall.
Yeah, well, you have to use finite numbers, otherwise
Mathematica goes boom.
Yeah, that's right. That's the problem. It's Mathematica's problem. They can't handle infinite coefficients. So the first thing I wanted to talk about today is just the first point, is that we found a difference. You noticed a difference yesterday between square roots and cube roots. The difference was square roots have plus and minuses and cube roots don't.
Cube roots just have the plus.
So today we found a difference between graphs of quadratics and graphs of cubics.
You can have
as long as you have real coefficients, and we're not going to get too complicated. With quadratics, you could actually have no real roots.
Yeah.
With cubics, you always seem to have at least one.
I wonder why that is.
That's pretty neat, right? So there's a difference. So we're going to start seeing some other differences soon. Okay, that's good for today. Good job, sweetie. Good job.